Hello guys, I see some questions coming in. I'm going to quickly shoot off this email and then we can chat about some chemistry. Okay, that's done. Okay, so hi, can you work through the problem from slide 3 today since you were only solved to find energy and not wavelength? Yeah, absolutely. Hello, could you go over how to do question 1 on the class day 5 practice problems? Yeah, absolutely. So what we'll do is go through the, let me see a second. Let me pull this up. So I need that up. I don't need that. I need that. That's done. Okay. And we don't need that. We don't need that. We don't need that. Don't need that. Don't want that. Okay. Back in here, back in here, and we're looking at the slides from today, which was day 5. Okay, let's share my screen so we kind of see what we're looking at. Okay. So this is where we ended up in class for YK, and what we basically saw was that the measurement that we have in joules, I focused in lecture on this concept of we want to make sure that we're following the units forward and seeing what the units mean, and sometimes when we look at this question here, for example, we can run into this trap of when I'm reading 4.1 joules per gram, if I just put in joules per gram, I need to immediately feel uncomfortable because I watch my units, I think about my units, and there's an aspect to this unit that has to involve a temperature unit. This constant, this specific heat for a certain object, specific heat capacity for an object is a constant. It changes what the object is. Water absorbs heat differently than air does, than metals do, and so that's what this term is doing. But we know it means the unit Celsius, and so we can kind of solve this. And so again, I can go to Wolfram Alpha, my online calculator, right? If I don't have a scientific calculator, this is a really great resource, but I'll say 7.4 e to the 5 grams. I'm going to times that by my constant, the thing that is relating how much of water do I have and how much of the temperature of the water am I going to change. I have a lot of water. I have a kid's pool's worth of water, which I've measured in grams. That's the green unit. And please, I know the recording is like 10 seconds behind or so. So you're going to see that if you have questions or you want to interject, please do. But it might take me a second before I come in and actually answer it for you. But feel free to stop me at any time. And let me get this a second. So we're going back to this. We're putting in our, we're changing it by 1 degree, whether we leave it as 27 minus 26. That's what I'll do for now. And we can equal this out. And now we have a unit in joules. And so let's go to one thing over here. And what is the question? Okay, so we'll say it is 3, or what is my, let's write this in. Again, I'm not going to spend a whole lot of time worrying about the significant figures, but I do want to spend a lot of time, I shouldn't say joules, but this is the unit is going to be in joules. And so this is some sort of energy. And so we're now going to kind of, let me make sure I can have my chat up. And before I go further, let me make a quick mark too on our Canvas site for what we're actually talking about. Okay, so let's edit this. And how long have we been on for? About 24 minutes. Okay, so great, I have my joules energy, and what else is my problem giving me? It's telling me the amount of photons, and they all have the same wavelength. So this is a very unique way to heat up a pool. I'm really not using a wide spectrum of light. I'm not putting in wavelengths of all different types, but I'm putting in one specific wavelength that's being supplied to this pool. I'm punching this pool with packets of energy that all have the same wavelength. And so if all of these packets of light that are hitting the pool, they're all the same wavelength, and I know how many of them are coming forward. And well, I kind of know. I know that's 26 moles. And so what I want to ask YK, the person who's asking me to go through this, and this is just something I do in office hours, both to make space for people watching it later on and to get you to do something, because it's not enough for me to just show it to you. You want to have a pen and pencil, you want to have a online calculator up, you want to have some way to kind of talk me through these things, because this is what I would do in my office. I'd make you grab a pen and kind of do it. So okay, great, this is the same. So I want to ask you, let's just work on the next part of the story problem. We know that we have quantified the amount of energy required to heat the mass of water by 1 degree Celsius. That's what we have. What's the next thing that we need to start messing with? Well, we have these atomic units. And so the next one is 26 moles of photons. And so what is a conversion factor, or what is something you know about moles? What do they represent? So if go ahead and put it in the chat, what do they represent? And let me write this out too. Right, and I'm going to highlight it with green. What is a mole? This is how I approach it, like a game. What do I know about moles? Yeah, we can. And that's really the only thing we can use is Avogadro's number, because we can ask ourselves, what is a dozen? Right? A dozen is just a grouping of 12 things. So what is a mole? We may have to add a little bit to it, but right, in this case, it is a number of a lot of things. So it's much bigger than a dozen, but it tells us how many punches are we delivering to this pool. Or that's how I'm starting to think about it, is I'm transitioning from saying this can be converted. I can mess with the units to say that if I have 26 moles of photons, this is not 26 punches. This is a lot of punches. How many punches? Well, I take the unit I don't want, and I'm organizing the way I'm approaching this problem to say I want to get rid of this mole. And so I'm going to write again moles of photons. And I know that if I have 1 mole of a photon, right, in the back of your head, you can remind yourself that if I have like 12 dozen photons, right, that would be 12 dozen. I'm going to kind of, and in 1 dozen of photons, you get 12 photons. And so this math, we kind of understand this. This is fairly easy. And so you're right, this is a term that we need because we're working at such a small scale that there are a lot of things going on here. And so we have to go into this and say, I'm actually describing a lot of punches. So let's take e to the 23 right off of this thing, but remind yourselves that these are exactly related in the same way that like this is kind of a centimeter. This is femtometers, kilometers. It's way, way bigger. They're both describing the amount of something. This is new to us, but we need it because we're working with so many photons, so many little things. And so mole is how we talk about it human to human with numbers that make some sense, but we use Avogadro's number to say, okay, now I know exactly how many photons I'm actually shooting out. And so if I do this calculation, I'm going to say that we have 26 times 6.022 e to the 23rd. And oh man, it's a big number. Thank goodness I can get it in scientific notation. I'll simplify it again. And so we're coming back to this. So let's say 1.5 e to the 25. So now I know how many photons that I actually am delivering. And so now we know how much energy is being delivered through all of the photons. So there's or let me say this. Let's pause for a second and ask another question, and I'll write it in as well. I'll say it and then I'll write it in. How do these two units relate to one another when we conceptually treat light as a particle? We want to know, or we know that we're delivering a, what does the text say? Okay. We know we're delivering photons that all have the same wavelength, and we know how much of them we're submitting to it, and all of the energy is being absorbed in it. So the question I want to ask yourself is, what is a relationship now So we've been playing this kind of game by playing with these units and figuring out how to get them to relate to one another. And so the first part of the problem was we had these measurements of distance. We were starting to feel like, how do we get from distance to grams? Well, distance to volume, volume through density to grams. So now I'm getting some amount of understanding of the energy and the temperature change for this pool. And then on the other end, and so let's write that in. So it was... All right, here's our number. So let's take this down. And so we have because we kind of want to conceptualize what are we saying here. We want to Oh, I can write it from this, can't I? So I'm just kind of reorganizing. I've messed around. I've played kind of some similarities or how I can mess with these units. So this is how I'm thinking about. I know all of the energy that the pool needs to change its temperature by 1 degree Celsius. This mass of water, how to heat up this mass of water, how much energy it takes. So I have an idea of an energy. And I want to start thinking about, well, how is this energy being delivered to the pool? It's being delivered in photons, which are really just things. So I have all of these photons gives this energy. How can I kind of change how I use words to describe this? So let's write that in. Because this is where if we're starting to not just try to find solutions and memorize all the different math units I can throw at you, we want to start thinking about what are we actually calculating. So how do I change my thought here? I need to talk about a wavelength. A wavelength describes one photon. Right now, and again, it's okay to say I'm not sure, and I can ask a different question. But how do I change my thinking around this? It's all of the energy and all of the photons are giving it. It's not like one wavelength is delivering all this energy at once. That's not how light works. Light is not delivering all of these joules of energy in one boom of light hitting it. Light has to send in all of these photons one at a time. So rather than thinking about all the energy from all the photons, what's another way to kind of reduce this thought or think down to something that will help me get further in answering this question? Yep, I like what you said. So we've had somebody who basically said, well, the number of photons are present when there's that much energy. Absolutely. But I want you to think about the problem that we're trying to solve. When we're asked to calculate a wavelength of the photons, that means each photon is bringing a wavelength of energy to it. So instead of thinking about all of them and all of the energy, if they come in bursts and packets in lots and lots of small punches, instead of thinking about how all of the punches feel together across all of the punches, what should I just focus on? This is kind of where we're at. We're saying if I do this enough times, there's this much energy. Instead, I might want to think about... I hope that read on the video. I know my video is a little small. I actually can change to full screen while we're chatting. I think I can. Where is it? Talking, maybe? Yeah, so right now we're saying my hand is going to tell you all the energy, and I'm sending all of the punches and saying all of these, tons and tons of punches together. My hand would report an energy. But if they're particles, how might we want to change our thought process? Or another way to think about these units that are on my screen somewhere. All of the energy from all of the photons, or instead of saying all, not all the punches of energy. How can I change this? And we're not changing units. We're not converting. We're just making sure we know what we're talking about. And it requires a lot of combining together, knowing what units are, making sure you have a physical understanding of what length means, what time means, what volume means, what energy means. And then, so now we got it in the chat room. The student said, and again, take the time to solve this as you're watching this recording, or jump to when I answer it at some point. But instead of thinking about all of the energy that all of the punches deliver to my hand, can I divide them all? I can say, well, each punch is delivering a piece, a packet of this energy. So let's go back to solving this. So, okay, cool. So I'm continuing to kind of really understand what units are, and I can say, okay, if I have all of these things, so if I have all of this energy, and let's say I have so I have 309-ish joules, and they're being delivered over how many packets? I think that's close. Yeah, it's close enough. Okay, and it's about... And so what's cute about this, in my opinion, what's cute about this is, what am I doing is I'm just going back in here and saying, okay, Wolfram Alpha, just do this calculation for me. I have all these joules spread over all of these photons. And if I bring it down to a number, then it says that I am getting, and let's put this in red, the number has come down a lot. And so the unit carries over. I am delivering all of these joules over all of these photons. But when I actually do the division of this much energy over this many photons, I get a number that tells me the amount of energy. But I have to remember it's per one photon now. I'm down to one thing. And I changed my descriptor of it because I'm just talking about things. If you have a dozen donuts that you're sharing among a dozen people, it's one donut per one person. You change it because we're down to the number one. When you get down to the counting of something and it's one thing, it is that one thing. So now we know how many joules that each photon is delivering. Now, can you bring now the fact that we know the energy of the photon? Can you give me a wavelength? Is there a relationship between energy and wavelength? And if so, how do we make that relationship? What constant do we need to relate how much energy is going to how do we get that to wavelength? And I'll happily put that in. But again, take the time in the recording to think internally as best you can, be wrong, have no freaking clue, and then listen to what I'm saying and see if you can follow my logic. But we now know how much energy is coming per one photon. We know all of them are delivering the same amount of energy. This should be converting to some sort of wavelength. But what's the last step for this? It's so cool. I love this question. So many different units, things going on here. Yeah, speed of light is going to help because we need one more. So what have you said? You have made it very clear to me that we know, what does speed of light do for us? Speed, I first thought of as miles per hour. I started to realize it's distance per time. And so if scientists need to use meters per second, I have an understanding of it, meters per second, but it relates distances to time. And that's helpful, but we're not done yet because we need another yes, the other constant we need. We need both of these to solve the problem. But there's another great constant. And again, I focus on how important the units are. This one, thank goodness, we can just understand because we've lived on Earth long enough and we've got our license and we've seen things driving, we understand speed. Part of chemistry is saying there's some other concepts, some other relationships you don't use in day-to-day life, but the chemist can, the physical chemist, can really think about some of these things. And so you're right, Planck's constant should be more than just a number. It's more than just the magic number you put in to get the answer. What is its units? And so Planck, he gave us a constant called H, which its units are energy seconds. It's energy seconds. And so if we have then an energy, if I know that it's about, if I know I'm delivering 2.06 e to the 19 joules, and I have this Planck's constant, I have something, so I just have to, how do I want to put this in? I take this idea that there's something in here that can convert, but I have to ask myself, what unit goes into this box that will cancel out and just give me joules? And I can make this even more clear. So we have joules here, and we have seconds there. How do I get rid of a second? And I won't wait for somebody to answer this, but I'll just say, well, it's in 1/2. It is second per. Where do we see seconds per? How are seconds per something that we should start to have an immediate, when I see seconds per, I want to have a pretty fast thing that comes to mind, especially when I'm at the quantum scale, because I'm noticing the good news is by using Planck's constant, I get away from joules and there's something with seconds involved. So I can start to see that now I'm starting to see where eventually I'll have to use the speed of light later, because the speed of light is now going to take me from time to distance, which is what the question's asking for. So the path is laid out for me that I have now an understanding of what energy each photon brings. If I know what energy each photon brings, Planck's constant allows me to transfer the energy to some form of a time unit, and the time unit through the speed of light is the time to the distance, and that's the answer they want. And so we need to basically we're solving for the last property that we talked about of a wave, something we can measure about a wave, and that is its frequency. And if we have its frequency, right, we have the relationship of, here's the combined relationship would be and so we can combine this all into one and say that the energy of the photon, right, this value, it's in joules, is equal to my h, which has units of joules times seconds, times the speed of light, which is meters times seconds, over top of a wavelength. Oh, let's do it better. And we have a whooper. And so this is kind of skipping ahead. I just want to get to the next student's question, but follow the units and say that constants can get me from energy to something to do with time. That's Planck's constant, joules and seconds, energy to time. What can I do with time? Well, time can be related to distance through speed. Speed of light is how fast a wave goes. That's how I can get the distance out of it. And so when we look at units canceling here, the seconds and the speeds per second would cancel out. Seconds and per seconds would cancel out. Meters over meters would cancel out. And I'm back to relating the units work out. I have this thing in joules on the end, but I can describe this amount of energy using Planck's constant, speed of light, and the length of the light wave. So I'll leave that there and say we've at least done a pretty good job. So that's 49 minutes. Okay, 49 minutes. And so moving on to Kay's question. Hey, could you go over how to do question 1 on the Class Day 5 practice problems? Yes, I can. So let's pull it up a second. Okay, Class 5. And just to check, are you still here, Kay? Checking, see if Kay's still here, just so I can talk. Yes, awesome. Great, 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 great. Okay, pulling it up. Okay, so, all right. So the question is, a hydrogen atom with its electron already in n equals 2 absorbs a photon of 486 nanometers. To what n level does the electron jump? Awesome. Okay, so what we have here is a question about, let me make a note. This is at 54 minutes. Practice problem 1 on worksheet 5. Okay, so conceptually we want to think about how this is my proton, and I have a theoretical, n equals 1 level where the electron could be, but it's not there. Instead, there's an electron that actually exists in this orbital, n equals 2. Heck, we can even maybe color code it. That's where the electron is. And there are other orbits where it could be. And this question is saying, oh, we don't even know. And it absorbs a photon of 486. So the first question I want to ask you, Kay, is that when I'm putting a nanometer in, when it's absorbing a wavelength, let me write this out. When it's absorbing a wavelength, how can I think about the how can I think about what I've done? I've absorbed a wavelength. Well, what does that mean in terms of energy? I take in 486 nanometers. What does this mean in terms of energy? I'm sending the nanometers in, and it's absorbing it. Do I expect that I'm putting in energy, or is energy coming out? Like, what's the deal with this energy concept? We just kind of spent some time saying that thanks to Planck's constant and the speed of light, I can relate this to energy, but I want to make sure we know what I mean by saying that I'm absorbing or I'm taking in 486 nanometers. We want to conceptually understand what does this mean, visualize it, and then see if we can solve it. Energy is being added to the atom. If the energy is the correct quantity, the electron will be moved to a higher orbital. If not, it'll be scattered. Awesome. And so but what's key to this understanding is that by putting energy into the system, there is an attraction, right? There is an attraction to the proton. And so when I'm putting energy in, when I take in energy, I'm actually pushing it further and further away. So it's going further away from things. I'm actually, if I choose the right amount of energy, I can push it further away. I have to pay energy to push it away from the thing it wants to be at. So when we're thinking about absorbing nanometers, we should think we're absorbing energy. If I'm absorbing energy in an electron-proton system, I'm paying energy to push it further away from the nucleus. And so what relationship did we see in class? What relationship did we see in class today that defined this for us? And more interestingly, as you're looking at my slide, if we are comfortable with the key concept from today, let me even pull it in again. Right? This even comes back here again practically. Which one of these equations is helpful based on the information we currently have? The second one, yes, awesome. So we're looking at how there's a relationship. If we know the right R, we can have this final and initial state. And so our way to start setting up this equation is saying that 1 over 486 nanometers is equal to R. We're going to have to choose the right R. Which R, and times it by 1 over our final state, which we don't know what it is, but we do know what our initial state is. And so our initial state is we're in 2 squared. And so if we find what R is, and let's look up what is R. I'm going to be embarrassed and probably not spell it right. And so, okay, great. Here's one. So we have one that relates it to, well, okay, meters -1. So this is kind of helpful. And so the R here is let me see if I can simplify it. So I'll simplify it to about 11 million, and we'll go into our, what is this, 11 meters -1. And then the next thing we would need to do is say to ourselves that the next problem is meters to nanometers. There's a difference here in our two or we're in the same family of still talking about distance, and it's all being in the divisor, but we still need R's to agree with one another. So let's take the constant of R and say, or maybe it'll be more conceptually, it'll make more sense for us to say, well, if I have 486 nanometers, I want to get rid of nanometers, and instead I want to follow whatever the unit is of my constant. And so I want to get to meters. And so 1 meter is equal to 1 e to the 9 nanometers. And so we'll take that, put it into Wolfram alpha. And we get 4.86 e to the -7 meters. Okay, great. I've now changed my length to meters equal to my R, which I'm staying as 11 million. Okay. That's one side of my equation. 3, 1, 2, 3. And let me see. Okay. And let's see. Okay. Huh. I'm getting x is equal to 2, but I don't think that makes a whole lot of sense to me. Unless... let me check something really quick. Oh, shit. Okay, this is actually something that I was mistaking a little bit. We have to actually be very specific with how we set up our orbitals, it looks like. Or sorry, how we set up our lines, because the change in energy is defined as the lower going to the higher. So I think that although this equation, let me pull this back up. Okay. I think I see why you're confused. You probably did what I did and ran into the same thing where you're like, oh, this doesn't make sense conceptually. It didn't to me either. So my issue is that I'm defining this as the final state minus the initial state, and that I'm always assuming my final state is, I'm always making the assumption that I'm emitting. This formula, let me make a note. And the more general one that I was looking at, I've actually, I have to, I'll need to look into this further a little bit to understand it myself. But I'm clearly not making a delta delineation the way I should be in here. It's not a, it is a delta, but it's not a delta like I'm used to seeing. So let me add this in here. This I think should work. We should test it. We'll see. I think that this one, I want to look into this a little bit more. Because what does it change? I'm using the same R infinity that I pulled from here. And how would it change my math? It would change where I put my X here. And let's see if that makes it a little bit easier. Or does that actually give us the answer? So is it that it should be 1 over the lower energy, and we know that we're absorbing it, so we're going to sum X squared. Keep my same R, keep the conversion that I did before, keep the same R that I did before, and that should work out. You're getting 0.46? I'm not sure if I agree with that number, but let's see. Well, I'm sure you're right, and then maybe I'm even more confused than I should be. Okay, and then... So if it assumes we emit light, does it assume our electron is dropping orbitals? Yeah, then our... But I still want to finish this one. If the energy of our lower energy orbit and the energy of our higher energy orbit, if we emit light... I bet maybe that might be it, actually. We're running into making sure we define positives and negatives correctly, and I don't think I did that very clear at all in class, because I myself am seeing that there are some issues here. So let me see what does the... Is that right? No, I think we are. Okay, let's try here then. Oh! I know what I'm doing wrong in my Wolfram Alpha. That's why I was just writing it wrong. Okay. Okay. Ha! Oh, we got it. Okay. Sorry. We're fine. I wonder if we're even fine the other way. Just because I'm very curious. Nope, it doesn't work. Interesting. Okay. So the error I made with... First, I did have this error of it is actually quite defined what is the two energy states. We always need to follow that it's not delta, it's... we always put the lower energy orbit first and the higher level energy second. And then when we actually do the math, if I do make sure I convert it, so this is me converting it to meters, and then I have to put it over 1. So now that it's in the denominator, I set it equal to my approximated R. I have the final energy is the lower energy state was 2. That is where it started. That's where it started, and so we're saying we know it's the 2 squared, and it's because it's absorbing a photon, it should be going to a higher level. So then I have my 1x squared. It has 2 solutions, either -4 or 4. We know that our energy levels are only these positive integers, so it is jumping to the 4th energy level, approximately. And solve for E using the wavelength. Let's try it. Again, though, it comes back to, I felt uncomfortable with this because this is initial minus or initial going to final, but I've always been trained that delta is final minus initial. So I might even have some misconceptions with what this delta E is, and we're going to need the Rydberg's E that has to do with energy, which, let's see if we have it. Oh, wait, here it is. Yeah, we might be able to. So let's at least entertain this. So how useful is this equation? I'm saying that this R value needs to be a unit in joules. There's my R value in joules. And so we'll take it again and... Okay, how does the other one do? So delta E is equal to 2.179 e to the negative. So you went back to the original equation and you were able to get to x equals 4 by switching your math. No, yeah, a little bit. I would say this, again, I'm going to leave it on the screen because this works for emissions. And if we assume we emit light, then our final state will always be the lower energy wavelength. So our final state will always be the lower energy if we're emitting. If initially we're a higher energy, we emit down. This would work for emitting, but this is a more generic formula that can handle both absorbing and emitting light. Same constant, and you have to make sure that, well, in this case, it's not about final and initial. It is actually about being very specific. The lower one comes first and you minus off the higher one. I did have to use this because if you pause the video, you'll see that I am putting the lower state and I know I'm going to a higher state that I don't know about. And so I'm solving for whatever the heck this is, this X, and it's 4. The second number, once squared, should be bigger than the first number. This is 2 squared. This is 4 squared. Okay, so what did I need? I needed this. No. Okay, so I can say 2.17 e to the negative 18 times, now we can see how useful is this, times 1 over my final energy state. That's what we're calculating for. We don't know what it is, and we know our initial state is 2 squared. And so, and now we take the energy we're putting in, because that's what this question is also giving us, is we have 486 nanometers. Let's bring this to joules. 486 nanometers. 1e to the, it was 1e to the 9, I think. Yeah. 1e. Oh, shoot, that's what else I'll have to memorize. Oh, no. Okay, 1e to the negative 9 nanometers is on 1 meter. Speed of light. Okay. Okay, so I'll simplify it to you have the speed of light is 3 times e to the 8 meters in 1 second. And this will give me, I'm converting this distance using speed to some sort of time understanding of it. So we got 486. Let's put them together. 486 divided by 1 e to the 9. And then we're going to times it by 1 over 3 e to the 8. And so now we have 1.62 e to the negative 15 seconds. We know that Planck's constant, right? Planck's constant, make sure we find the right one. Okay. So there's our joule second value. H is equal to 1.05 e to the negative 3 joules times seconds. And so this is going to then say that, well, if I want to convert my value, I can take the concept that the wave, or what I'm effectively kind of saying is that the speed of light, which is meters per second, if I have this and I, divide it, let's say, well, no, I don't want to do it that way. If I have a wavelength in meters and I divide that by meters, no, I don't want to do that. Times 1 over meters per second. Or what am I? What? If the speed of light, let's make this a little more clear. So if the speed of light is equal to meters per second, and a wavelength can be converted to meters like I did up here, and I try to say there's some equality of this the speed at which this thing is going over time is equal to the wavelength of something times wavelength to this concept of frequency. And so as long as my units are all meters and per second, I'm able to find the relationship of these things. And so kind of what I've done over here is I've done the conversion first, and then I've divided by It's a little bit foggy, but I'm trying to explain kind of what I did up here. I'm saying that if I know the wavelength and I divide it divided by the speed of light, which is meters. I should make that clear that that's still in meters per second, is going to bring my second frequency on top. So right now, I don't want to necessarily use this value, but instead I want to use 1 over this value to represent the frequency that I'm going to need for the next conversion of joules per second. So when you see me do this calculation that you saw in red, and I'm getting a number out that's 1.62 e to the negative 15 seconds, in my head, I'm very quickly saying, I know this relationship in my head. I kind of did some algebra and moved some things around, obeying algebraic rules, but the value I'm getting out is seconds, and that's not what I want to describe. I want to describe it in per second, so I'm just dividing it over 1 to get per seconds. And so then I'm going to go back to taking Planck's constant, kind of move that up. Okay. And so I'm going to times this by 1 over So I'm going to times this by 1 over 1.62 e to the negative 15 seconds, because I need to get a value out of this in joules. Again, we can kind of return to what we saw earlier. This is this combined formula where I could have just put in the nanometer again and done Planck's constant times the speed of light divided by my wavelength and got a similar answer. But this is me kind of just showing us how I'm working through the units and how the units have to make sense. And so let's go into Wolfram and say, okay, we've got 1.05 e to the negative 3 Planck's constant times 1 divided by this number that I just calculated. I gotta be careful here. Let's be a little bit more specific. This is H. We're calculating now for just the energy in joules, And so it is, energy is equal to, big number, 6.48 times e to the 11 joules. And then we're back to this equation. I now know the energy, so let's see how this does. 6.48 e to the 11 is equal to 2.179 e to the negative 18 times 1 over x squared minus 1 over 4. No, it's not following the same progression that I was expecting it to, I guess. Unless I put it in wrong, which I don't think I did. There's something about this constant that I don't think I even understand. So what do we do then in this case? I think I want to make an announcement just saying, I think this is the only way we know how to treat these things. I wish this worked, though. It should work. I don't have a good answer for this at this office hour. I'm going to have to look into it myself a little bit. I think we're going to have to go a little bit more into this is the formula we're going to tend to use, and there's something I'm misunderstanding about the constant and the way they're defining the change in energy. Because I think this is coming back to something in physics that I still have some issues with always understanding how we define things coming in and out. What's the system and what's the observer or what's the surroundings. So I apologize for this. Is at least it'll be interesting for people to go through because they'll be like, why is it so long? But I'll send a note out tomorrow about and I'll even present very quickly at the start of class. At least saying check your email to make sure you read this from me because it is more complicated than I suspect. I know that I believe that there is something about these relationships that is true, but I'm misunderstanding that these are possibly meant for only emissions. And because I think that these two formulas are very similar to one another, I think again that this formula is breaking down because of emissions. Let's even check. I don't think it'll fix it, but we'll see. No, it's totally broke. Yeah, I don't know. I don't feel great about that, but let's see. Okay, yep. Thank you. And really, it is just I myself am not explaining it as well as I should. And guys, I do have to get ready for my rehearsal, but I will be back again tonight when that is done. So come back with more questions, keep struggling with this thing, and if I have time, I'll try to look into this and see if I can at least do like a more helpful lecture around this stuff. Hour 31. That is bonkers. Here N2 must be greater than N1. Here the final energy state, or N2 always has to be, maybe this is my misconception. Yeah, this is my misconception. I didn't realize that this is only for emissions. This note is really important. So anyways, let me post the helpful one and I'll try to figure out more about what's the difference between RH and R infinity. That means something. There's something that's being baked in those constants that I'm not understanding, which then means I need to make sure I transition that to you guys. So keynote, boom. This is actually quite important. It is this works for emissions. It's not going to work for anything else, and it's the same freaking unit. What the heck? Okay. Awesome, guys. Thank you so much, and I will see you guys on the flip.